Okay, welcome to Notes at 23, where we continue our discussion in Chapter 5, and in particular Section 5.2. Remember, Chapter 5 talks about determinants, which I already said, they're good, they're interesting, but they are a lesser topic than some of the things that we've been talking about and some of the things that we will talk about. So useful, but not the biggest of the ideas that we're talking about. So let's just get through these and get on. Determinants are not my favorite thing. They just seem like, okay, you just wing around these numbers, you get something, and it tells you something, but or you can use it to compute something, but it doesn't really give you terribly much insight into what's really going on in linear algebra, from a more systematic way, and those are the things that I think are the real important things. So let's get on with this. So we've already talked about how we can find a determinant from the pivots, and that's actually, if you were to use MATLAB to calculate the determinant of a matrix, it would actually find all the pivots and then multiply them to give the determinant. But there are some other ways to do this, and they crop up every once in a while in material, in electrical and computer engineering. So you ought to at least have been exposed to it. But in reality, these days, if you need a determinant of a matrix, you're going to have your calculator do it or have a computer do it, and that's the bottom line. But you should be aware of these things. So there's something called the big formula, and it involves permutations of columns. And if there's n columns, there will be n factorial different ways of ordering the columns. So there's n factorial permutations. And so when we say big formula, we mean big formula, as we'll see in just a little bit. There's something called the Cofactor Formula, which may pop up here and there in some of your further studies. So you should at least be familiar with it. And basically what that does, it's kind of an iterative approach to things. It says, well, you want the determinant of an n by n. You can write that in terms of a bunch of determinants of n minus 1 by n minus 1. And then you can keep going. So now you got a bunch of n minus 1 by n minus 1 determinants. You can write those in terms of a bunch of different n minus 2 by n minus 2, and so on and so on. And you get it down to a bunch of 3 by 3s, and those you can do by hand with the trick that I showed you in the last set of notes. And by the way, that trick of tacking on the last two columns and then doing three diagonals left to right and three diagonals right to left, or also left to right, but left upper to right downer, and then three diagonals from left downer to upper right. That only works for 3 by 3s, so you can't extend that to 4 by 4s or higher. Anyway, so in the old days before you had calculators, if for homework problems you would use these cofactor formulas to find determinants. But again, these days your calculator can do it, and MATLAB can do it for you. But nonetheless, it's worthwhile knowing about these formulas, because sometimes you'll run across them in a book or something. So here's a quote-unquote example. It's really more of just a foreshadowing. So here's the textbook author's favorite matrix, and he's just pointing out here that we can find the determinant three different ways. We can do row reduction to get the pivots. We can apply this so-called big formula, or we could use cofactors. And again, continuing on with this, but not really as an example, so to speak, but more just kind of illustrating where we're heading with this, because we don't know the big formula and we don't know how to use cofactors. But what we'll see is that if we were to convert this particular matrix into LU form, so we look at the U matrix and look on the diagonal, we'll have all the pivots. We would find that these numbers that are being multiplied here are the different pivots, and they all multiply to be equal to 5. And notice we'll take advantage of this special form for this matrix in just a little bit. Notice that the 2 cancels, the 3 cancels, the 4 cancels, and we're left with 5, which is our answer. So that doesn't always happen in these pivots. It happens for this nice matrix. Yet another cool thing about this particular matrix. We'll use that to kind of illustrate some ideas later. Since this is a 4x4 matrix, we already said the big formula involves the number of permutations of columns, and the number of permutations of 4 columns will be 4 factorial. So there's 24 different terms, but it turns out for this one, since there's 3 zeros up here and 3 zeros down here, only 5 of these 24 terms will end up being non-zero. And so those 5 terms will boil down, and we'll see where these things come from later. 16 minus 4 minus 4 minus 4 plus 1. So there's the 5 terms, and they add up to 5 in this case. And the 16 comes from the diagonal. So if we just do the product down the diagonal like this, we get the 16. And then the trick that we'll be talking about is how to get all the rest. So there will always be that diagonal term involved, because that's the one permutation that's easy to see. Permutation of the columns in their normal order, 1, 2, 3, 4. But we'll go into more detail in this in just a little bit. We're just foreshadowing what's happening here. And then we can also, for this particular matrix, use the cofactor method. And in this case, the cofactor method just boils down to a simple computation for this particular matrix. So we'll look at these in just a little bit. But these cofactors, which we're seeing here as the 4 and the 3, are just 2 of the 4 possible cofactors for this matrix. They come from looking at 3x3 determinants. So remember, I said the cofactor method is kind of an iterative approach. You break a 4x4 down into a problem involving a bunch of 3x3s, and we know how to do 3x3 determinants, so we can stop there. But if this were a 5x5, we'd break it down into a bunch of 4x4s, and each of those 4x4s would get broken down into a bunch of 3x3s, and then we would evaluate those 3x3 determinants. And we'll see how to do that. So let's just talk about the pivot formula. We've already talked about how if we have a diagonal matrix, the determinant is the product along the diagonal. And so if we can do the LU decomposition, the U ends up with the pivots along the diagonal, and therefore we just have to do a product of those with a little adjustment sometimes. So this is based upon the idea that the determinant of A, if A can be written as L times U, the determinant of a product ends up being the product of their 2 individual determinants. And in this case, since A is equal to L times U, it's just the product of the pivots. So the D's here are the pivots. They would be the diagonal elements in the U matrix. So that's when A can be written explicitly as L times U. But sometimes, as we've seen way back at the beginning of the course, we saw that sometimes we need to do some row exchanges, and that involves a permutation matrix. And so sometimes it's not A that gets written as L times U, but it's P times A, where P is a permutation matrix, gets written as L times U. I think we already talked about how a permutation matrix will have a determinant of either plus or minus 1. And so that's where this plus or minus comes from out in front. So to use this approach, all you have to do is find the pivots and multiply them together, but then you have to account for whether you needed a permutation matrix to do row exchanges or not. So here's a very simple example where we don't even have to work to get the decomposition once we do the permutation. So we start off with A, and we recognize that we've got a 0 here, which violates our setup for doing conversion into LU form, and we also see that we have a 0 here as well. So we need to do a row interchange, and so if we put the third row up at the top, and if that's all we do, if we just interchange the top and the bottom, we end up with a perfect scenario. So now we end up with numbers down the diagonal. This is already in upper diagonal form, so our L in this case would just be the identity matrix, and we had an odd number of row exchanges, and we saw earlier in an earlier set of notes that a single row exchange causes a sign change. In fact, any odd number of row exchanges causes a sign change. An even number of row exchanges does not. And so now we can account for this. We do this product 4 times 2 times 1 gives us 8, but then we account for the negative, and so the determinant of the original matrix would be -8. So we've just seen that the pivots give the determinant, but the determinants can also be used to find the pivots. So that's kind of an interesting backwards version of this, and we'll illustrate this here and motivate this with our beloved matrix with 2 down the diagonal and -1 down the minor diagonals. And we've already worked with this matrix many times, and if you do the row reduction on this or convert into LU, you'll discover that these are the pivots. And so here is the LU decomposition of this. Here's the U, here's the L, here are the pivots down the diagonal of that. So I've just rewritten that here on this slide so we can continue. And so we know that the determinant of this 4x4 matrix, as we've already seen, is 5. It's just doing this product, and the 2's cancel, the 3's cancel, and the 4's cancel, and we're left with 5. So it's kind of a clever little structure there. So that's for the 4x4 version of this matrix. Now there's a clear structure to this matrix. As I said, 2 down the diagonal, -1 down each of the next off diagonals. Suppose we looked at the 3x3 version of this. So let me just clear some of this stuff off. Suppose we were only interested in this matrix and just looked at that, the 3x3 version of that, we would get the similar kind of thing, and in fact we would end up with this kind of form. And I think it's pretty clear that once we've done row exchanges, finding the determinant, or finding the LU decomposition, kind of progresses from top to bottom. So this thing, which doesn't require any row exchanges, would lead to this same structure up at the top. It's this stuff that's needed to do the last step of the decomposition or the elimination. So this would be what arises from the 3x3, and again we see that the 2's cancel, the 3's cancel, and we end up with a determinant of 4 in this case. And we can generalize this and say that if we have an n by n matrix of this form, not any matrix obviously, but of this form, 2's down the diagonal, minus 1's down the two closest off diagonals, the determinant of that matrix will be n plus 1. And in general, we see that our pivot factors end up having cancellation, and that last n would get canceled from the previous term, and we're left with just the n plus 1. And so that's just illustrating a structure for this matrix that shows that it's easy to compute the determinant that way. But in general, we didn't really prove this, but we're trying to motivate it here, that the first pivot depends only on the upper left corner of the original matrix A without row exchanges. And in other words, to kind of extend that, the first k pivots come from the k by k matrix AK in the top left corner of A. And again, here we're not, we're kind of assuming we don't have to worry about row exchanges. But we know that we can always handle the row exchanges by just dealing with signs. So let's not worry about that right now. So the determinant of the submatrix AK, which is that upper left corner k by k matrix, will be a product of k pivots. So those are the diagonal values down the U matrix for that k by k submatrix. And so if we think about it, let's just work from this direction. Let's say we take the determinant of AK over the determinant of AK minus 1. So these are the upper left corner. So we're taking a k by k version in the numerator and a 1 smaller version in the denominator, just a k minus 1. So k minus 1 by k minus 1 in the denominator. And if the top is k by k, it will end up having a product of the pivots, and the bottom will have a product of its pivots. But as we said up here, those pivots will be the same. So, so these actually cancel. The D1 cancels, the D2 cancels, and the dk minus 1 cancels. And what are we left with? dk. So what this big yellow box is telling us is how to find pivots from determinants. So that's kind of useful, especially now with easy access to calculators and computers that can do determinants. Instead of having to do all the row reduction stuff to find pivots, we could just take a bunch of determinants and take their ratios. So you calculate the sequence of determinants and then just start looking at the ratio of two adjacent determinants, and that will give you the sequence of pivots, which is really kind of cool. So, and we can also kind of use these if we look at the a sub k's, and if all the a sub k's are non-zero, then we know that we don't need to do any row exchanges for this particular matrix. But if one of those determinants is 0, then we need to rethink and consider doing row exchanges. So I'm not going to go into the details on that. I think you would kind of know how to do that if needed. But again, as I'm saying, all this determinant stuff is secondary stuff. My opinion. Other people may think differently, but I think most people would agree that in linear algebra, determinants are cool, and they're interesting, but they're not the big idea that you should be focusing on. So let's talk about the big formula for determinants. You hardly ever need to use this, but it's kind of interesting to see it. So we've already seen that pivots are good. If you ask a computer program that is designed properly for finding determinants to find you a determinant, it will compute it by first finding all the pivots and then using those pivots to find the determinants. And we've also seen, yeah, I guess I don't really need to say that. So what I'm trying to say here is that we've seen that pivots are good. Pivots are good for computing the determinant, but sometimes it's kind of interesting and useful to see how the determinant connects directly to the elements rather than from the pivots, which come after you've done a bunch of row reduction. So we'd really like to find some sort of explicit formula for the determinant, so that you say, here are my elements of my matrix, and someone could, if they wanted to, calculate what those are. So that might be useful if you're trying to determine, I mentioned that sometimes the determinant is used as a characterization of something that you're trying to accomplish in the design of a system that's characterized by a matrix. I alluded to that, and that I used that in some of my research, trying to find the area of an ellipse that I could bound by a polygon, like a rhombus or something like that, or actually a parallelogram. And I might want to know, if I change this one element, how am I changing my determinant? So in that sense, this formula would provide a really key insight into that. So unfortunately, it's called the big formula because it's big. It can be potentially big. In my application, the matrices that I was dealing with were pretty small, so they were 3x3s at most, and so characterizing it in terms of the big formula wasn't terribly bad. So this formula has n factorial terms, and look how fast that grows. So n equal to 1 gives us 1 factorial, 2 factorial is 2, 3 factorial is 6. So in my case, I had a 3x3, so I only had 6 of these terms in this big formula to worry about. But then look how quickly it goes. 4 is 24, 5 is 120, and if we go out to even just an 11 by 11, there's 40 million terms, roughly. But I mean, at 40 million, who's going to argue if you if you just round off to by a couple thousand? So 40 million terms, that's a lot to consider. For the n equal to 2 term, we've already seen the 2 terms that are involved, AD and BC. That's our beloved formula, or they're in our beloved formula for the 2x2 determinant. And just like we see for the 2x2, we saw that half of these have a negative sign and half of them have a plus sign. We also saw for the 3x3, our little trick, we got 6 terms. Sorry, that shows us here. So in a sense, that little trick is doing this big formula, and it's just a clever way of forming these 6 terms, and we saw that 3 of them had negative signs. The ones that go from the lower left to the upper right were the negatives, and the ones from the upper left to the lower right were the positives. So let's see about this big formula and see how we can get it. So let's start with n equal to 2. We already know that the determinant is equal to this. But we'd like to see, for this case where we know the answer, kind of a nice systematic way to get there. Then we can take that systematic way and extend it. So what we're going to do is break up each of the rows. So there's the top row, AB, written as a sum of 2 rows where each of the component rows has a 0 in one location. And then we're going to break up the second row that same way. And so working with this first decomposition form, we have the so-called linearity, the row linearity of a determinant. So now we can say, well, the determinant of this matrix is equal to the sum of these 2 determinants. That's just the row linearity result that we saw earlier being applied. And so now we can take each one of these and we can break up the second row using this second rule, or not rule, but the second decomposition. And so now the first term here gets broken down into two terms following the blue arrows, and then the second term gets broken down into two terms following the brown arrows. And so now we've got 4 terms, and that comes from 2 to the 2. Let me clear off some of this ink here. So the last line ends up with 4 determinants, which is 2 to the 2. But because of the zeros that get introduced here, a bunch of these are going to be 0. So in fact, two of them will actually be 0. So this one will be 0, and this one will be 0, if you think about how to compute those 2x2s. So we're left with just this one, and we then end up being able to pull out, again using the linearity idea, we're multiplying A and D times these elements, so we can pull each of those out, and we're left with essentially the identity matrix. We can pull the B out and we can pull the C out, and we're left with kind of the flipped identity matrix. And then, so these are permutation matrices, and we know that their determinant is either +1 or -1. So this is the identity matrix, so it's +1, so we get plus AD. This is identity matrix with 1 row exchange, so that's going to be negative. So we've just, again, proved this formula, AD minus BC. So our 3x3 determinant, if we follow that rule that we talked about in the last set of notes, where we tack on the last, we tack on the first 2 columns at the right, and then just do these diagonals. That's the formula we came up with. And remember, this formula is only valid for a 3x3, and that trick is only valid for a 3x3. But let's take a look at this pattern here. So notice that each product has 1 entry from each row. So we've got a 1, a 2, and a 3. A 1, a 2, and a 3. And every one of these products, the first index is 1, 2, 3, 1, 2, 3. We've ordered them that way to make it easy to follow. So what that says is that we can walk in order through the rows. But notice what happens to the columns. So we add 1 entry from each column, but in all the different possible orders. So as we go through the rows, 1, 2, 3, we'll always do the rows in that order. The columns can take all the possible orders. So we've got 1, 2, 3 on the rows, and we've got 1, 2, 3 on the columns. Good. All right, that's 1 term. Second term, still going 1, 2, 3 on the rows, but now we're going to do some other order of the columns. 2, 3, 1. Okay, we got that one taken care of. Still the same order on the rows, 1, 2, 3, but now the columns are going to go 2, 1. Oh, that's wrong. Should not go 2, 1, 2. Should go 2, 2, 1, 3. Because notice that we can only take each column once. So this should be A12, A21. So let's see. Let's make sure we get this. That should be this term is the first one. This is the second one, which takes us down to there if I brought it over. Then I've got A13. That's the problem. A13, A21, A32. So it's this one that's the problem. That should be a 3. I will try to fix that in the notes before I post them. Then we've got 1, 2, 3 for the rows, and we've got 1, 3, 2 for the columns. And then we've got 2, 1, 3 for the columns, and we've got 3, 2, 1 for the columns. Let me just make sure all of those are right. 1, 2, 3. 1. We should have 3, 1. We're going backwards now. Yeah, something isn't quite right here. I'm going to need to check this formula. And it might be incorrect on the previous slide as well. So I apologize for that. But the idea is that we should have every combination. So if you remember, we're going back this way. We're now going to have, so we have to count them in the order of the rows. So we've got 1, 3, 2, 2, 3, 1. Okay, this is right. That's that term. Then we've got this term, which will go up through this one. So that's going to be 1, 1, 2, 3, 3, 2. Yeah, so it is correct. But the point here is not whether you get this formula, whether you have it memorized or not. The point we're trying to make is that as we go through the rows, we'll always do the rows in the same order, but we have to take every possible permutation of the columns. And half of the signs are negative, so we need some way of figuring out which terms end up being negative. And so why do we have 6 terms here? If we follow that same approach of breaking this into rows, simpler rows, doing the row linearity. When we had a 2x2, we had to break each row into a sum of 2 rows. But now with a 3x3, we're going to break into 3 rows. So it'll be, A11, 0, 0. Then it'll be 0, A12, 0, and so on. So 3 rows, or 3 terms, each one with just a single non-zero element. And then we would have to do the second row split that way, and do the third row split that way. So we end up with 3 to the 3, or 27 simple determinants. But if you go and look through all of these, a bunch of them are going to be 0. Only, and they'll be 0 only when the non-zero terms come from different columns. So there's 3 factorial or 6 different ways to order the columns. So the key is that we can only draw from different columns. If we try to draw a pair here where a term here that has the same columns, then that determinant actually ends up being 0. That's one of the terms here that ends up being 0. So I know this is kind of hard to follow. I'm less interested in you knowing precisely how we go about doing this. This is all going to fall out into some formula. And to be honest, normally I don't say this, but at this point, really just understand what the formula is telling you to do, and that's good. So it turns out that half of these 6 ways come from odd permutations, and the other half are even. So we get half plus signs, half negative signs. So let's just take a look at this. So I suspect that my error has crept over here as well. So this needs to be the number 3 here, but I think everything else is right. 1, 3, 2, 1, or 2, 1, 3, 3, 2, 1. Yeah, so everything else is okay. These are the 6 terms that would come from doing this to a 3x3. All the terms that are not shown here explicitly would be 0. So all the other determinants that would make up the rest of the 27 terms that would come out of this, using the linearity trick, They'll all go to 0. And so then what we can do, doing the next step, is factor out each of these terms. So we factor them out in front, and we leave just a bunch of 1s behind. We factor these things out, and we leave a bunch of 1s. We factor these things out, and we leave a bunch of 1s, and so on and so on. And so now we're getting all these determinants are determinants of permutation matrices, and therefore the result of that is going to be either +1 or -1. And so from this, hopefully you can kind of see where this formula comes from. So we've got the columns, we've got n columns, and we need to look at all possible permutations of the numbers 1 through n. So we're going to write that as alpha, beta, blah, 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 out to omega. So just imagine these are just dummy variables filling in for the possible values that we can take. So for one permutation, alpha would be equal to 1, beta would be equal to 2, and we just put them in order all the way out to n. Another possible permutation would be alpha would be equal to n, beta would be equal to n minus 1, all the way out to 1, and all other possible permutations as well. And so here's what we do. Let me clear some of that ink off there. From row 1, we're going to take alpha, or A1 alpha. So we've got an order here. So now we're going to go through the rows in order and the columns in each of these possible orders. So we're going to go 1 alpha, 2 beta, 3 gamma, all the way out to n omega. We just went through the rows. Now we're going to find the next reordering of the numbers 1 through n, and we'll go 1, that new alpha, 2, that new beta, and so on. So it's a little confusing, and I'll help you see how to do this in just a second for a 4x4. So what we're really doing is choosing one entry from every row and column. So we have to get every pair. And what we're doing is we're just doing that systematically. We're saying we're going to go through the rows in sequence, and as we go through the rows in sequence, the columns will follow some permutation value. And the way we write this formula is like this. So we're summing over all n factorial possible column permutations. So there will be n factorial terms here. And this is just our selection of elements out of the matrix, where we're going rows in order and columns following some appropriate permutation. And this is what the big formula is. So in other words, again, choose one entry from every row and column. Now, as an example, if we took an upper triangular matrix and you were to try to think through this, there's only one way, one permutation of columns that will get you all non-zero elements. So every other permutation of columns as you go through the rows in order will get you something from the lower part of this upper triangular matrix, which will make that product be equal to 0. So there's only one term, and that will be the product of the diagonals. Which we know already. So the big formula is consistent with what we've seen already. So that's nice. All right, so here's the example, 4x4, that will hopefully illustrate how to do this big formula. So this is our favorite matrix. And the big formula tells us that since it's a 4x4, there, in general, for a 4x4 will be 24 terms. But we do notice that there's a fair number of zeros in here. So a bunch of those 4 factorial terms will end up being 0. And so the trick is figuring out which ones are 0 and which ones aren't, and then only worrying about the ones that aren't. So it turns out that there's only 5 terms that are non-zero. We've seen this result written out already, and I promised that you would see where this comes from, and we already alluded to the fact that the 16 is down the diagonal. So we know that. That's taking the rows in order, taking the columns in order, take us down the diagonal. So that's the most obvious term that's going to be in there. Where do all these other terms come from? Such that the result ends up adding up to 5. Let's figure out where those all come from. And it basically boils down to choose one entry from every row and column for each term. So there is a neat command in MATLAB called Perms. Has nothing to do with hairstyle, has to do with permutations. So I put in the integers 1 through 4 because I wanted to see all the possible permutations of the numbers 1 through 4. And if we back up, remember there should be 24 terms, 24 permutations of 4 elements. That's 4 factorial. So if we come over here and you look, this array of numbers is the result of running that perms command. Now I did one other command, and this is kind of a cool command to know about. It's called flipped, or the best way to think about it is flip up down. And there's a related command called flip left right. So when I ran this perms command, it gave me the permutations in an order I wasn't terribly happy with. All these 4s were up at the top and the 1s were down at the bottom. And to be honest, the order that it, even with the flip up down, is still not exactly the order that I would think about, because I would want this one to be right at the top. But I thought about doing a bunch of manipulation to make that happen, but I gave up and said, well, all right, I'll just do the flip up down to at least get the first column to be all the 1s, to start with all the 1 value in the first column. Anyway, those are all 24 possible permutations. And now what we're going to do is figure out which ones end up being 0. So remember, what we should think about is up at the top, let's put a 1, 2, 3, and a 4 up at the top. That's the order of rows we're going to take. So if we take this set of numbers and match it with each one of these other numbers, it's going to tell us the order of columns that we take for those rows. So the first thing I'm going to do is go through this one, which will give us a non-zero result, and it will actually give us this result. So these circles here are showing the elements that are being picked. So this result gives us this one. And so what is that saying? It's saying take row 1, column 1. That's this. Take row 2, column 2. That's this one. Take row 3, column 3. That's this one. Take row 4, column 4. That's this one. And the product of those is 16. So that's one of the terms that's in the big formula. Okay? So that's that one. Let me clear some of this stuff off here. So remember, 1, 2, 3, 4, that's the order of the rows that we're taking. Now let's look at why I've crossed out a bunch of these. So let's get rid of all the 0, all the terms that will be 0. So notice I've got this big red rectangle around this one. So remember, this is row 1, and it's all the permutations that would take row 1, column 3. Well, what's row 1, column 3? It's that number right there. So every combination, every permutation in that box is going to have this element in it, which is 0. So all of those are gone. Notice also row 1, column 4. That element is 0. So all of these permutations, regardless of what we get from these will be 0 because of this first element. So all of these are gone. And those are all gone because of those two elements. And then we can go through and do similar kinds of things. So let's do this. So let's look at row 2, column 4. Well, row 2, column 4, that's also 0. So anything that's row 2, column 4 will end up having a 0 term. So that's that one and that's those. Okay, so we got rid of row 2. Row 3, column 1. So I need to go down this column here looking for places where I have a 1. Well, there's 1, but I already took care of that with row 2. So there's 1, so that one's gone. And there's other places where it occurs, but it's already been annihilated because of previous things. Okay, now let's go down to row 4. I've got column 1 and column 2. So there's a column 2, there's a column 1, so those are gone. And you know, there are places where those also occur, but they've been previously annihilated. So I've now crossed off everything that I don't have to worry about. And the things that aren't crossed out are the only ones that are non-zero. And there's 5 of them. We've got 1, 2, 3, 4, 5. And every one of those is shown over here on the right with the selected elements circled. So we've already done this one. Let's do this one. 1, 2, 4, 3. Remember, rows go in order. So it's row 1, column 1. That's there. It's row 2, column 2. That's there. It's row 3, column 4. That's that one. And then it's row 4, column 3. That's that one. So if we do that product, 2 times 2 times minus 1 times minus 1 gives us a plus 1. Why do I have negative 4 there? Well, because if we look at the permutation matrix corresponding to these locations, so it would be zeros everywhere that's not circled, and where it's circled, the permutation matrix would be 1, 1, 1. That permutation matrix has one row exchange, so it's an odd number of row exchanges, so it's negative. And likewise, if we do this for all the other ones, you can track through every single one of the other ones will match to one of these. So we would have 2 times negative 1 times negative 1 times 2. That gives us a plus 4, but there's only one row exchange here, so we get a negative. This also gives us a positive 4 product. One row exchange gives us a negative. Here we get a minus 1, minus 1, minus 1, minus 1. So negative 1 to the 4th gives us a positive 1. And it remains a positive 1 because there's this row exchange and there's this row exchange. So there were 2 row exchanges to get this matrix from the identity matrix. Or that, not that matrix, but the permutation matrix. And so here's all those terms. So that's the big formula. Will I ask you to do that on a test? Probably not. It would be, first of all, it would be a nightmare to grade. But you ought to just give it, a little practice, but don't spend a huge amount of time on it. Cofactors. So this is a method that you may encounter some discussion of this as you go into some higher level ECE classes. Basically it's saying, the big formula is great, allows you to see how everything folds into the determinant, but it's pretty big to digest. And so the cofactors idea allows us to just use a single row to separate out some lower order determinants. So remember, we alluded to the fact that this cofactor approach basically starts with a n by n and breaks it down into n minus 1 by n minus 1 problem, a bunch of them, and then we can apply that again, and we can keep taking it down to lower and lower order matrices or determinants until we can do them by hand. So that would be 3 by 3s. So we've seen this formula here, and yep, that error is just carrying through all of these places, so that should be 3. And let's see what happens here. Do I end up getting that right? Yes, this should be, I believe this, let's see, A11 gets factored out of those two. I think it ended up getting corrected down here. A12 gets factored out of those two. A13 gets factored out of these. Yeah, so it's correct down here. It's just not correct up there. So what we're doing is we're factoring out the elements from the first row. So the first row elements, we've written them as the first term in each of these. So there's an A11 there and an A11 there, and when we factor it out, these two terms with the negative sign come down here, and so on. So we get three terms like this. And you can see that these things inside the parentheses look like, gee, they could be determinants of a 2 by 2. And in fact, they are. But we'll call those things cofactors. So just rewriting that formula here so you can see it, these cofactors end up being 2 by 2 determinants that are coming out of row 2 and row 3. Notice that everything inside the parentheses has has only elements in row 2 and row 3. So the first index has to be either 2 or 3. 2, 3, 2, 3, 2, 3, 2, 3, 2, 3, 2, 3, 2, 3, 2, 3. So that is correct. And the first row contributes all the factors out in front. So we have factors and cofactors. So let's see how this all works. So here's a 3 by 3. Now we already know the answer to this using that little 3 by 3 trick that I showed you in the previous set of notes. But here's how we would do this. So you identify this A11 is one term, and we're basically going to say set all of these things to 0. So this is just applying the row linearity kind of idea. And so if we add these three matrices together, we'll get our original matrix. And so the linearity of this allows us to break this out like this. But notice what we've done here. Let me clear some of this off. I mean, that's theoretically how we get there, but from a mechanics point of view, what we do is we imagine picking for each element out of the first row that we pick, we imagine zeroing out all the other elements in the column and row of the selected row 1 element. That's what we're effectively doing theoretically. And if you look carefully at this, you don't really have to, but you should be able to see, if you did look carefully at this, that we're really still choosing one entry from each row. So, and we can see that that's true because it ties back to our previous result. But here's what we really do. We have to watch the signs on this, and the 2 by 2 determinants that we end up with, we find by doing this. We say, well, we think about taking the one that's going to be our factor for that term, and we nuke everything else, and we say there's the 2 by 2 determinant that's left. Here we take our factor, which will be A12, we nuke everything else and take the remaining 4 elements as a 2 by 2. Then we nuke everything here and take the remaining 4 elements as a 2 by 2. And so we can see that the 2 by 2 determinant that goes with A12 would come from these 4 elements, and we would think that it's going to be A21 times A33 minus A31 times A23. So that's what the determinant of that looks like. But if we go back and look at what we really get for that term, here's our A12. Look carefully at this. It's the 2331 that comes with the positive sign, but over here we're saying, oh, that actually, if we just talk about just the determinant, has a negative sign. So that term has to have a negative sign attached to it. So we need to reverse the sign of the cofactor C12, but not for the other ones. So here's the rule. We cross out row 1 and column J to get a submatrix M1J, which will be of size n-1 by n-1. We find its cofactor, which is the determinant of that submatrix, and we have to adjust its sign, and we multiply it by -1 to the 1 plus j. So remember, -1 raised to an odd power will give me a negative sign. -1 raised to an even power will give me a plus sign. So this is just going, as I go through the j's, so as I go through the columns, it's going to go, when j is equal to 1, it'll be -1 squared. So it's going to go, this one gets associated with a plus, this one gets associated with a minus, this one gets associated with a plus. And if we had a bigger matrix, it would just keep alternating, plus, minus, plus, minus, plus, minus, and so on. So this is the formula here for figuring out the cofactors, their arbitrary determinant value, and the proper sign to attach to it. Now there's a trick. You don't have to really do this -1 to the I plus j. You can just think about this checkerboard. So you always start in the upper left corner with a plus, and then everything alternates from then on. So plus, minus, plus, minus. Now you come down, come back here. You don't alternate from minus to here. You alternate from plus here to minus, then plus, minus, plus, and then I had a minus here, so I go plus, minus, plus. So you never have either going across a row or down a column. You never have two same signs in a row. So they always alternate. So you get this checkerboard that looks like that. And so now you just use these signs to apply to the determinants of these. And so the cofactor expansion along row 1, you just take the elements along the row, you figure out their cofactors, which involves just crossing out the right column and row to take the determinant of the remaining elements, look at our checkerboard to get the sign, and put all that in as the cofactor. And if you don't like row 1, you can use this for any row that you want. Now, why would you not like row 1 but like some other row? Well, what if row 1 has 4 non-zero elements in this 4x4 case? In the n by n case, what if it has all n elements equal to 0, but there's some row that only has 2 non-zero elements? Go for that row, because then you're only going to have to do 2 cofactor evaluations. So you kind of scan down through, find the row with the fewest non-zero elements, and go for that row. Now, when you pick a different row, you're going to have to pick a different row to figure out your signs. But other than that, everything else is exactly the same. So here's the formula. It looks exactly the same. We're just doing the ith row instead of the first row. So this gives us the 2x2 formula, actually. So we can say A, what is its cofactor? Well, its cofactor is a 1x1. So the determinant of a 1x1 is just D. And since that's in the plus position, it's going to be A times the determinant of the submatrix, which will be D, and a plus sign out in front because of the plus sign. Okay, that's good. Next, oops, sorry about that. Did not mean to do that. Meant to, I have no idea what I even did there. I'll have to explore that some other time. Next cofactor would be B, or next element in the first row would be B. So the submatrix is just C. Determinant of C is C, but this is in the negative position, so we get the negative sign there. So that works for that. Here's an exercise for the 4x4. Obviously, we would not want to pick row 2 or row 3, but row 1 works. Row 4 works equally well. So, the numbers in the first row multiply their cofactors. So we're claiming that if you do all the cofactors, you'll get a 4 for that. Then if you do, let me clear this off here. If you do this one, the cofactor for that will be 3, and so on and so on and so on. But once we start multiplying by zeros, it's really only those first 2 cofactors that matter. So why would we even bother computing those? So we're going to have the first element 2 times 4, and then technically these are the cofactors without the signs. So then the next one would be, actually no, I'm sorry, there is a negative sign there, so those cofactors are correct. So then we would have a -1 times a 3, and that's why we get the negative sign there, and we get our 5. So those factors come from the 3x3 determinants that would arise from this. So to look at this in a little bit more detail, so that was just kind of a quick and dirty way of looking at this example. Let's look at it in a little bit more detail. So the first row is a good row to look at because it's the one that has the fewest non-zero terms. So we're only going to need 2 cofactors, C11 that corresponds to this non-zero element, and C12 corresponds to this. C13 would correspond to that. We don't need it. C14 corresponds to that, and we don't need it because each of those will get nuked by that zero, by the corresponding 0. So what we're going to do is take the 2. Let me clear this off here. Clear off the ink. We're going to take the 2. It's in a positive position, so we just take plus 2 times, there would be a 0 up here, obviously, and a 0 down here, times this determinant. It's a 3x3, so we can do it. We can do our down here. We can do this, and remember, this is going to continue on over into here, and then we're going to have this, which, remember, continues on over into here. It's just a way of doing these determinants in place. So those 2 terms end up being 0, those diagonals, and then we get a 0, we get that term which is non-zero, and we get that term which is non-zero. And if you work all that out, you'll get the result that we said. And likewise, there would be a 0 here and here and here for that term. And so you can evaluate those, and you get 2 times 4 minus a -1 times a -3, which ends up being 5, which we know is the result. So like I said, these are nice things to know how to do. They're not the biggest ideas in the course, but something you should at least be somewhat familiar with. So if you go on to a subsequent course and somebody says, oh yeah, so here's a 4x4 matrix, you could find the determinant of this by cofactors, you'll know how to do that if you needed to. But in reality, most of the time you'll be using computational software to calculate determinants, and just expected to know what those will tell you. So we'll stop here, and I'll see you in the next set of notes. I think that's the last one. The next one is the last one on determinants, and then we can go on to something more interesting, in my opinion, and probably in lots of